Greetings to one and all present here. I, Gautam Kumar, one of the authors of the paper titled Comparative Study on EEG Datasets using Neural Networks and Traditional Machine Learning Models, am here before you to present our work at the International Conference on Cognitive and Intelligent Computing 2021, hosted by CMR College of Engineering and Technology, Hyderabad. Before I start, I would like to thank the members of the Advisory Technical Program and Organizing Committee for making this conference possible during these challenging circumstances. I would like to start with a brief introduction followed by specifics of the work done, then the results, and finally with the discussion and conclusion. EEG is one such biomedical signal that is obtained from neurons, cluster of neurons, or brain regions using single electrode arrays or scalp electrodes as shown in the figure on the left. It has high temporal resolution in the range of milliseconds, but it is low in spatial resolution as shown in the figure on the right. Here two systems, one with a 32-channel EEG headset and another with a 64-channel EEG headset as shown in the figures left and right, were used to record the EEG for the data used in the study. EEG is recorded either as a resting state where the participant or patient is looking at a fixed cross or a fixed object on the screen, or a task wherein a stimulus is provided and the response is expected from them. Usually it is done as N trials where a number of those stimuli are repeatedly presented, or in case of a staircase where a range of stimulus is provided before an optimum level is identified for each individual. This EEG is then pre-processed based on several steps such as filtering, removing line noise, artifact detection and removal such as eye movements, eye blinks. Bad channels that were present during EEG recording are replaced with algorithms that process or average out the EEG from surrounding electrodes. Finally, event-related potentials are then computed for each of the specific stimuli, and a neural correlate between the stimulus provided or the resting state is then obtained based on the EEG signals. In this work, three specific networks, both in terms of functional and structural network of the brain, are studied or examined using the machine learning models. We have the default mode network, executive function network, and the attention network. The names or the brain regions are on the left and the corresponding cognitive functions or behavioral functions are on the right. EEG is usually studied in terms of spectral power analysis, functional connectivity, or complexity measures such as entropy-related techniques. When it comes to spectral power analysis, the rhythm bands of specific frequencies are computed, analyzed, and then provided as input for machine learning models. In terms of functional connectivity, the electrodes become the vertices or the nodes of a graph, and the synchronous activity or asynchronous activity between these nodes becomes the edge parameters. Based on this, either you have a directed or undirected graph or network, which can then be studied based on centrality measures or edge properties of these said networks. Entropy methods such as approximate entropy or permutation entropy values are provided as features or inputs for machine learning models. In this study, two EEG data sets from the Open Neuro repository is used. One is from Parkinson's disease study, another is a meditation study. Below are the 5 machine learning models that were implemented here to understand how they perform based on these two EEG data sets. The UC San Diego resting state EEG data from patients with Parkinson's disease is one of them, which has 31 participants, of which 15 are patients, 3 sessions, a baseline, a state where the medication for Parkinson's is provided to the patient, and a state where the medication was not given. They had to focus on a fixed mark on the screen, and it is a 32 channel EEG system that was used. In case of the meditation study, a 64 channel system was used, wherein 3 questions were or stimulus were provided to the participants and responses were collected. Here we had 12 expert meditators and 12 novice or non-expert meditators. Here's a brief pipeline of the analysis or processing of the way EEG was carried out and how it was given as inputs to the machine learning models. Download the data set, find the specific events. In case of resting state, 300 millisecond windows were used. In case of the meditation study, the response to each one of those questions were taken. These epochs were then were given as input for calculating the spectral connectivity using the coherence equation. These matrices then were converted as data frames for input into the learning models. Here you can see the equation that was used and the frequency that was used, that is 0.1 Hz to 45 Hz. The entire pipeline for this part was carried out using MNE Python package or toolbox, and the implementation of the learning models was carried out using scikit package. These are the 5 models that were used or implemented. These are the classes, the clusters, or a brief about each one of them. In case of SVM, there were 3 classes: healthy controls, patients with meds on, meds off. And in case of the meditation group, we had 2 class, experts and non-experts. In K-means, we had 3 clusters, and in case of the meditation dataset, we had 2 clusters. Deep convolutional neural network had a 3D matrix as input. 2 different layers were used: a convolutional layer, a pooling layer, and a fully connected layer. In case of RNN, we had used the long short-term memory, which had 256 memory units, a dense layer with a sigmoid function, a dropout layer which used the LSTM layer, and binary cross entropy for loss, and the optimizer used was Adam. In case of graph neural network, the PyG 2.0 package was used. Here's an illustration of SVM and RNN that was implemented. These are the results. As you can see, that DCNN performs slightly higher or better when compared to both data sets. K-means failed to provide decent results, and GNN failed because there was an issue with memory overflow. Here's the overall accuracies for both of these, and here you can see the K-means clustering, where the red dots indicate the centroids. As you can see, off-the-shelf approach doesn't work for K-means. It requires more filtering or processing of the data before good accuracies can be obtained. Machine learning has been used in biomedical signals for classification and prediction. Applications range from electrocardiograms, electromyograms, and MRI data or imaging data. In case of classifying pathological states and healthy states, or also predict the rate of progression of the disease and possible impact of intervention programs are used. ML on EEG in terms of brain-computer interface has been fruitful in helping creating hardwares that understand EEG for home automation or wheelchair control. Here we see that deep CNN provides good results when compared to the other 4 models. Increasing the number of electrodes does increase accuracy, but so does the complexity and time required. And as mentioned earlier, graph neural networks failed due to memory overflow in the off-the-shelf approach. Here we were able to look at the impact connectivity measures such as spectral connectivity, specifically coherence matrix has. A comparison of the classification accuracy of all 5 machine learning models were carried out. Preliminary evidence on respective ML models for EEG data with minimum pre-processing has been shown here. We also carried out mini-batch k-means clustering as compared to k-means and showed promising results which required further investigation before it could be reported here. I thank the committee members for giving me an opportunity to present our work at this conference. Please feel free to mail me the comments or questions that you may have to the email ID provided at the start. And any comments and questions with respect to the implementation of the machine learning models can be mailed directly to Ms. Shraddha Dubey. Thank you once again for this opportunity.